In this video, we are going to begin a very interesting topic in engineering mathematics, which is Laplace Transforms. Laplace Transforms. It's a topic in engineering mathematics, and I see it as a very, very interesting one. Alright, let's talk about Laplace Transform. The Laplace transform of a function f of t, written as Laplace transform of f of t, is the integral from 0 to infinity of e to the power of minus st into the function f of t dt. This is the Laplace transform of f of t. F of t is the function of t. S is a parameter, and it is considered to be a real number. Alright? Let us take some elementary functions. For example, when f of t is equal to 1, what is the Laplace transform of f of t, given that f of t is equal to 1? The Laplace transform of 1, I'm going to write 1 now for f of t, is simply the integral from 0 to infinity of e to the power of minus st. F of t is 1 times 1 dt. So this is the integral from 0 to infinity. 1 times everything here is t e to the power of minus st dt. Now, remember the rule of integration. When we're integrating the exponential function, what is the integral of e to the power of x? The integral of e to the power of x dx is the same as e to the power of x, plus c. Remember, the integral of e to the power of kx dx, in this case now, x has a coefficient. The coefficient of x here was 1, right? So, if it is not 1, if it is, let's say, a negative value or a number greater than 1, what we normally do is to write ex, e to the power of kx divided by that k, you get it, plus c. So, you see the reason why if I had divided by 1, here, I'll still get e to the power of x. So, since t here is the variable in question, the integral of e to the power of minus st dt is simply e to the power of minus st divided by the minus s, which is attached to the t. You get it? Minus s from 0 to infinity. Alright, so definite integrals, we plug in upper limit minus plug in lower limit. So this is simply plug in the upper limit. By the way, minus s is a constant, right? So I can bring it out as minus 1 over s into e to the power of minus st from 0 to infinity. So what do? We plug in the upper limit, minus 1 over s into infinity enters here, we have e to the power of minus infinity. Of course, infinity will stand in for t. Minus s times infinity is infinity. Then we'll now say minus, plug in the lower limit, 0. This is minus, if I multiply 0 by s, it will give me 0. So if I plug in 0 here, everything here becomes 0. 0. E to the power of minus infinity is 0. So this is minus 1 over s into everything here is 0 minus e to the power of 0 is 1. Anything to the power of 0 is 1. 0 minus 1 is what? Minus 1. So minus 1 times minus 1 over s is positive 1 over s. So the first Laplace transform that we've gotten is that the Laplace transform of 1 is actually 1 over s. And the Laplace transform of a constant, for any constant, let's say k, of course, the Laplace transform of 2 will be 2 over s. For 3, it's still 3 over s. You can work it out. You're going to get it. Because this one here, if it is let's say 2, the 2 will come out to stand as a constant of integration. Then the normal integration process will still remain. You get it? So, by extension, the Laplace transform of k, which is a constant, is actually k over s, provided s is greater than 0. Now, let's take another function, the Laplace transform. This is number 2 now. This is number 1 of e to the power of at. You know, the first function we took was when f of t equal to 1. So in this case now, we are saying that f of t equals e to the power of at. Let's take the exponential function. The Laplace transform of f of t is this. So if f of t is e to the power of at, I should write e to the power of at here. Alright, so the integral becomes the Laplace transform of e to the power of at is the integral from 0 to infinity of e to the power of minus st into f of t is now e to the power of at dt. So we have this as the integral from 0 to infinity. These two have the same base, right? E. So bring out one of the base. Now I should be adding their powers. Minus st plus at. Since they are multiplying each other and they have the same base. So I'll just take one of the base, then add their powers. But t is common to both. So I can write this as minus s plus a into what? Into t. Do you agree? Yes. So this is minus s plus a in brackets into t dt. Alright. Now, following the same process of integration we followed in the first case, okay, this, if I integrate e to the power of minus s plus at dt, I will get e to the power of minus s plus a into t divided by this minus s plus a, which is the coefficient of t, minus s plus a from 0 to what? Infinity. Now, minus s plus a is a constant. I can bring it out. This is 1 over minus s plus a, alright, into, I'll be having this left. So plug in the upper limit minus plug in the lower limit. If I plug in the upper limit, I'll be having e to the power of minus s plus a into infinity, alright, then minus, plug in the lower limit, e to the power of minus s plus a into 0. Infinity times everything here gives infinity. Yes, then e to the power of infinity is still 0. So this is 1 over minus s plus a into everything here is 0 minus everything at this top here minus s plus a into 0 is 0. Because if you multiply any number by 0, you get 0. Then e to the power of 0 is 1. Because anything to the power of 0 is 1. So this is minus 1. So what would this give me? Everything here reduces to negative 1 all over minus s plus a. But you know what? This is correct, but I want to break this down into something simpler. This negative sign can actually come down. I guess you know that. It can come down like this. 1 over minus into minus s plus a. If this minus outside opens this bracket, we'll be having 1 into s minus a. You know that the s is negative here before. So times it by a negative value becomes positive. Then plus a times minus 1 is minus a. So everything here reduces to what? 1 over s minus a. And this is equal to the Laplace transform of e to the power of at. We have gotten 2 of them before. Why this is another one we've gotten, which is the Laplace transform of e to the power of minus e to the power of at. Don't forget to subscribe, like, and share it with your friends and to your classmates. Let's handle the next one. I think it should be number 3 or number 4 now. Number 3. Yeah, what is the Laplace transform when f of t is the cosine of at? Yeah, we have Laplace transform for cos at and cos sine at. What I'll do for just one of them, which is this one, the same principle apply, but just a different Euler formula. Watch. Now, for the Laplace transform of cos at, remember, Laplace transform of f of t is actually the integral from 0 to infinity of e to the power of minus st into f of t dt. F of t now is cos at, so I'm writing cos at dt. Alright. To do this, I'm going to make use of the formula we call the Euler formula. Using Euler formula. The formula is for cos 80, for cos 80 is equal to e to the power of I80 plus e to the power of minus I80 all over 2. Then for the sine, take note, let me write it here. For sine 80, it is e to the power of I80 minus e to the power of minus I80 all over 2I or I2. So the only difference between the two of them is just, you see, there's a minus here, and there's I attached to the 2 here. So I'll use this one to prove for the Laplace transform of cos 80. Then you can work on your own with this one. You follow my procedure, okay? So that the Laplace transform of cos 80 is this, the integral from 0 to infinity of e to the power of minus st. Now cos 80 is this, alright, my e to the power of I80 plus e to the power of minus I80, alright, all over 2 of us. So that over 2, I'll just not bringing my constant out. It can come out as 1 over 2. You get it? dt. So let's expand this bracket, 1 over 2, into the integral from 0 to infinity. Then if this multiplies this, it's going to be e to the power of, they have the same base, so out of their powers. T is common, so it will be minus s plus ia plus ia into t. You get it? Then this multiplies this, is going to be plus e into minus s minus ia into t dt. I hope you get this. It's very easy to do. Since they have the same base, okay, when you are multiplying them, just add their powers. And since there is a variable that is common to both powers, I just factored out the variable and wrote what is left in brackets in both cases. So let's perform the integration now. So this is 1 over 2 into the integral from 0 to infinity. The integral from 0 to infinity. Okay, let's just integrate. We have it as this. If I integrate everything here, okay, it's going to give me e to the power of minus s plus ia into t. You have to be very, very careful. Divided by minus s plus ia, minus s plus ia. Then plus, integrate this. We're going to get e to the power of minus s minus ia into t all over minus s minus ia. The integral is running from 0 to infinity. Alright, let's proceed. It's very important sometimes you know how to derive the Laplace transform of some elementary functions, because maybe in the exam you may be asked to do so. This is 1 over 2 into okay, what I want to do now, I can do anything depending on what I want, but let me just plug in the upper and lower limits at once. If I plug in the upper limit here, you know, we've seen before that e to the power of infinity is 0. So if I plug in infinity here, everything here becomes 0. Plug infinity here, everything here becomes 0. So if the upper limit enters this function, everything becomes 0. So just write my 0 plus 0 minus, plug in the lower limit here. If 0 enters for t, everything becomes e to the power of 0. And e to the power of 0 is 1. So I'll be having just 1 over minus s plus ia. Then if 0 enters here, everything here becomes 1 because e to the power of 0 is 1. Then I'll be having plus 1 over minus s minus ia. You get it? So this is 1 over 2 into, there's a minus here. That minus, let me just bring it outside since it's affecting everything in brackets. So I'll be having 1 over minus s plus ia plus 1 over minus s minus ia. Take the LCM of both. The LCM is the product. Minus s plus ia minus s minus ia. Alright, if you divide this LCM by this, we are having minus s minus ia times 1 minus s minus ia. Divide the LCM again by this, you have minus s plus ia times 1, that's minus s plus ia. Alright, so we have minus 1 over 2, minus s is minus 2s, minus ia plus ia is 0. Alright, let's expand this. Minus s times minus s is s squared, minus s times minus ia is minus s, that'll be plus sia. Ia times minus s minus sia. Ia times minus ia is minus I squared a squared. You get it? So what would this give us? Alright, let me erase this part of the board. 2 will cancel 2. Minus times minus will give me a plus. So I'll be having s all over, alright, s squared, right? Then this is s squared. Sia minus sia is 0. I squared, in complex numbers, I squared is minus 1. Alright, so this is now minus 1 a squared. Minus 1 a squared. And what does this give me? Plus a squared, right? So this is plus a squared. And this is actually the Laplace transform of f of t when f of t is cos at. We've gotten another one. Remember the first two we got before. So if you do for sine, take note, the Laplace transform of sine at is a over s squared plus a squared. Take note, this one is for cos, this one is for sine. You can follow this same procedure to do for sine. Now I've given you Euler's formula to use. You get it, so you can do that. Now, is it also possible to determine the Laplace transform of hyperbolic functions? Yes. You know, I've given you the Laplace transforms of cos at and sine at using one Euler's formula. Alright, so we also need a formula here, alright, for hyperbolic cosine and hyperbolic sine. Take note, hyperbolic cosine of s of t, or let's say t, that's cos t, is e to the power of at plus e to the power of minus at all over 2. Then for the hyperbolic sine function, that's sine at, it is e to the power of at minus e to the power of minus at all over 2. That's it for the hyperbolic sine and cosine. So what is the Laplace transform of? I proved for cos at initially, cos at, and I just gave you the Laplace transform of sine at. So let me prove for sine at. You get it? Sine at. Now it's going to be the integral from 0 to infinity of e to the power of minus st. F of t is now sine at dt. So we have the integral from 0 to infinity of e to the power of minus st. Then for the sine at, it is this. It is e to the power of at minus e to the power of minus at all over 2. Let me bring that 2 out. You get it? Dt. Alright, so what will this produce? 1 over 2 into the integral from 0 to infinity. Multiply this till you get e to the power of minus s plus a into t, then minus this times this e to the power of minus s minus a into t. Integrating this function, we have 1 over 2 into, if I integrate this, I'll get e to the power of minus s plus a into t all over minus s plus a. Minus, integrate this, you get e to the power of minus s minus a to t all over minus s minus a from 0 to infinity. Alright, so let's plug in the upper and lower limits. If I plug in infinity here and here is 0. We did that before. Plug this 0 here, I'll be having 1 over minus s plus a left. Plug this 0 here, we're having 1 over minus s minus a left. So we have 1 over 2. This minus can come out, so leaving us with 1 over minus s plus a minus 1 over minus s minus a. What's the LCM? Okay, so see what I can do. These two have minuses, right? So if the minus comes out, they'll become plus. That minus will times this one to give me a plus. You get it? I factor the minus out to times this one here, and they become positive. So this is actually negative 1 over 2, negative 1 over 2 into the LCM is the product of the two of them, minus s plus a, s plus a. Divide the LCM by this, you have s plus a times 1, that's s plus a. Divide the LCM by this, you have minus s plus a times 1, minus s plus a. So this is minus 1 over 2 into s minus s0, a plus a, 2a. We have 2a all over minus s times s minus s squared minus s times a minus a times s plus a times a squared. 2 cancels 2. We have minus a all over minus s squared. Minus as plus as is 0, so I have plus a squared left. But you know what? This is correct, but the minus should come down. We have a all over. If the minus comes down, this minus s squared becomes plus s squared. This plus a squared becomes minus a squared. This is the Laplace transform of the hyperbolic sine of at. So the Laplace transform of sine at is a over x minus a squared. Now, I don't want to prove for cos at. I want to prove the Laplace transform of cos at. But for the Laplace transform of cos at, it is this. For cos, it is simple. Let me say, Laplace transform of, this is number 5, let me call this number 6. The Laplace transform of cos at is similar to this. But remember we did for cos was s over s squared plus a squared. And when we got for sine was a over s squared plus a squared. So check this. For this and this, this is the Laplace transform of, this is the Laplace transform of sine at. This is the Laplace transform of sine at. What's their difference? It's just the minus. So this is the Laplace transform of cos at. Then for cos at, I will change this plus to minus. It is s over s squared minus a squared. That's it. Now, we've seen 6 of these Laplace transforms. I have to do one more. Don't forget to like, don't forget to subscribe, and don't forget to share this to your friends and to your classmates. So the next one, what is the Laplace transform of t? Alright, Laplace transform of t to the n. Let's discover the two of them. Now it's number 7, I guess. Let's get the Laplace transform of t to the n. From there, we will now get the Laplace transform of t, raised to the power 1. And we can now say for the others, raised to the power 2, raised to the power 3. Alright, the integral will be the integral from 0 to infinity of e to the power of minus st. F of t is t to the power of n dt. You get it? We are going to reduce this integral into the integral that looks like the gamma function. Let's go ahead. What I'll do here is I'll say let s be equal to st. Alright, I want to replace st with x. Differentiating both sides with respect to t, differentiate this ds dt. Since I'm differentiating with respect to t, differentiate t to get 1 with respect to t. 1 times s is s. And this means that the s equals s dt. Alright, from here, I have dt. I will make dt the subject of the formula. This means that dt equals ds over s. Let's keep this. From here, let me make t the subject of the formula. From here, t will be equal to x over s, right? So this integral will transform into the integral from 0 to infinity, okay, of e to the power of minus, what's st? St is s minus x. What's t? T is x over x. X over s. Alright, then n is still there, n is still there. The t is now the s over s. The s over s. Right? The s over s. Alright, let's expand this integral. This is the integral from 0 to infinity, e to the power of minus x. Then this is xn. You get xn over xn, dx over s, dx, over x. So I can simplify this to get the integral from 0 to infinity of e to the power of minus x. Then this is xn dx all over. This one is raised to the power 1. They are the same base. So if you multiply them, it will be x to the power of n plus 1. You get it? So we said that x is a constant, assumed to be a constant. So I can bring this whole denominator outside as 1 over s n plus 1 into the integral from 0 to infinity of e to the minus x, x to the n dx. So what do we do from here? Remember, I had a video for gamma function. The gamma function of x is the integral from 0 to infinity of t to the x minus 1 e to the power of minus t dt. This gamma function. So what will be the gamma function of x plus 1 from here? It's just to replace this x with x plus 1. So we have the integral from 0 to infinity of t to the power of x plus 1 minus 1 e to the power of minus t dt. 1 minus 1 is 0. So we have the integral from 0 to infinity of t to the x. You get it? Then e to the minus t dt. It's similar to what we have here. You get it? So it's similar to what we have here. This one now is, how did we get x? Alright, this one, in this case now, my x is t. You get it? X is standing in place of t, xt. You get it? So this integral now is, we can say gamma of n, because n here is replacing x. I hope you understand the language I'm speaking. We have x, we have t. So x here is t here. It does not matter. Variables can change. So if this one is the gamma of x, where x is the power here, right? This one is the gamma of x plus 1. I'm having x here. So what would this be? It means that this is 1 over Sn plus 1 times the gamma of n plus 1. If everything here is x and everything here is n plus 1, x plus 1, gamma of x plus 1, and this integral looks like this. So the main difference is that my x is t and my n is x. So this will be gamma of n plus 1. That's the meaning. Now, in gamma function, actually, if you want to understand the basic principle behind it, you can watch my video on gamma function. Alright? In gamma function, the gamma of 5 is 4 factorial. You get it? The gamma of n is actually n minus 1 factorial. That means we subtract 1 from this value that is inside the bracket. So the gamma of n plus 1 is actually n plus 1 minus 1 factorial. And that's actually n factorial. Do you get it? Yes. So this is actually 1 over s n plus 1 times everything here is n factorial. So if you multiply this, you will get n factorial over s n plus 1. And this is the Laplace transform. This is the Laplace transform of t to the power of n. We've gotten it. Here's it. So for t raised to the power 1, the Laplace transform of t raised to the power 1, which is t, will be plugging 1 here. 1 factorial. 1 factorial is 1 over s squared. That's it. Because 1 plus 1 is 2. So the Laplace transform of 5, of t to the power 5, will be 5 factorial over s to the power of 6. Full stop. That's it. So it's as easy as this. So you take of this and think of this as well. So this is where I will end the proof of our Laplace transforms of elementary functions. Alright, so I don't want to make this video very long. I'll stop here, and the next video I'll be solving examples based on these transforms that we've gotten. Subscribe, like, and share this video to your friends and to your classmates. Very important. I will see you in the next one. Just keep following, just keep watching.